All right, so far we've used conditional probabilities to calculate what are called a priori probabilities. The probability of A given B. B has happened. So what is the probability that A will also happen based on that? Now we take a look at a posteriori probabilities. Posteriori, posterior, behind, like looking back in time. Probability of A given B. A has happened. What is the probability that it was caused by B? So let's take a look at what's going on here. So the probability A given B. We know A has occurred. Track back. Did B cause it? Start off with how many options do you have for your event that has happened? In this case, we're looking at 2. A partition is dividing up the sample space into mutually exclusive, aka disjoint or non-overlapping events, but their union of all of them unions to the entire sample space. So a mutually exclusive union accounting for the entire sample space. That event B that we're wondering whether it caused it, have that interacting with the partition, let's go into partition B as well. I'm claiming that A intersect B and A complement intersect B, that they are mutually exclusive events and that their union makes up all of B. You may have seen a distributive property for distributing an intersection across unions, and that would be true whether the union is of mutually exclusive events or not. What good does that do us? Particularly the fact that these two are going to be mutually exclusive. Well, when we find the probability of B, since the set B, or the event B, is equal to what we see on that second line there, and we have mutually exclusive, that allows us to add to get the probability of all of B without worrying about double counting. No subtracting to worry about. A little rearrangement of things there. And next, we have recently seen with conditional probabilities that we can relate those probabilities to the probabilities of intersections. So I'm going to do a little substitution here. And then I'm going to substitute what we just found into the formula for conditional probability P of A given B. So here is the formula when we define the probability of A given B. Plug in what we found for the probability of B down in the denominator. And in the numerator, the same kind of substitution we did just before this in the PowerPoint, relating the conditional probability to the probability of intersections. And that's our formula for Bayes theorem when our partition involves just 2 things. We're going to look at 2 examples using that in just a moment. And then a 3rd example where the partitioning of sample space is into 3 mutually exclusive events. So keep on watching what's in the playlist.